Today we're going to look at some generative models for creating images. This will be the example I'll be focusing on. But I'd like to note before we start that these models are not exclusive for images. In fact, the examples we've been seeing so far for convolutional networks have been focused on images because this is the main motivation for these models, and also a very intuitive way of understanding how they work, but they can be applied to other kinds of data, for instance, time series, three-dimensional data. There are many variants there. However, today we're going to keep looking at this on the perspective of processing images, and in this case generating images, and I'm going to talk about two different methods. An autoencoder method, the variational autoencoder, that can be used to generate examples, and generative adversarial networks, which is mostly a method for training a generator network that involves adversarial training. So training against another network that is trying to find if the examples generated are real examples or artificial examples. So let's start with the variational autoencoder. We saw last week how autoencoders work. We use a network that has this kind of symmetry and some way of constraining the hidden representation there. For example, in an undercomplete autoencoder, this would be by having a lower dimension in this latent representation, but we can also use regularization. We can combine the different methods, but the idea is that this first part of the network, the encoder, is translating or transforming the input from the space where the input examples are, for example, the set of cat images, into this latent representation that has some attribute. For example, it's a lower dimension, or it focuses on specific features and so on, depending on the kind of autoencoder that we use. And then the decoder can translate back into the original space. So one question is if we can use this ability of the decoder to translate from this latent representation into the space where the examples lie, to generate new examples, so to generate new images of cats that are not exactly like any of the images in the training set, but still look like cats. So if we have an image of a cat, we can use the autoencoder to create this latent representation, and then we can use the decoder, but in that case we will obtain the same image. If the autoencoder is properly trained, it will be the same image or very close to the same image. The question is whether or not we can find some example here that is not present in the training set, but it would still create a cat image, a different cat image. So let's go back to something we covered last semester in machine learning, this difference between discriminative and generative models. So a discriminative model is trying to approximate a conditional probability distribution of the output y given some input. So what we have, for example, here in the decoder is that given some value here, we obtain an output over on this side, so an output on the network, and this network is approximating this probability distribution of the output as a function of the input value that we give it. When we have a generative model, we actually have a joint probability distribution of the output and the input, so that we can sample specific inputs based also on what output we have. For example, we saw the naive Bayes classifier that uses this approach, tries to estimate the joint probability distribution. We can use that to classify, but we can also use it to generate new data. And basically what we need, if we have this discriminator here, so this discriminative model, if we also have a distribution, a probability distribution for the input, then combining the two together would give us the ability to generate new examples, because now we can choose how to generate them. So basically with autoencoders, suppose that we have, this should be a Z, not an H, but suppose that we have the probability distribution of the values in the hidden representation. So if you know how this hidden representation is distributed, combining this with the model we have here that gives us the conditional probability of the output based on some input. So basically the decoder can do this. This should be a Z, not an H. If we also have an idea of the distribution of the space in that latent representation, then we would effectively have everything we would need to generate new examples. So this is the intuition here. We need to have a way to correctly sample the latent space, that is, know the distribution here, in order to pick something that will be translated into the kind of things that we want. So we could make sure that we would choose a value that would be translated into a cat, or maybe we knew different distributions for different types of cats and things like that, and so that we could generate the images according to what we want. If we don't know this, then if we just pick something at random, it's likely that we fall outside the set of representations, of hidden representations that are meaningful for this network, and so what we get out is garbage. So this is the problem. You cannot, if you train an autoencoder, it may be hard to use it to generate examples because you don't know the shape and the distribution of the latent space representation for the values that actually result in some meaningful outputs. So if you just pick at random without knowing how to select, you are likely to just get something that doesn't work. It's not the kind of examples that you want. Okay, so we can think of both the encoder and decoder as modeling conditional probabilities. So basically the encoder is giving us the hidden layer, the latent representation, so that hidden representation in the autoencoder as a function of the input, and then the decoder will give us the output. This should be a Y, not an X. There are some typos here. It should be as a function of the hidden representation. It gives us a Y, this output, which actually in the autoencoder we also want it to be the same as the input, the way it's training. But we can imagine here that we can be using this to generate some new examples. So basically we can use this decoder part to generate examples, to approximate the joint probability distribution of the hidden representations and whatever types of examples that we want, if we have this additional information, the distribution of the latent representation here, so that we can sample in the right places and not get some results like this. So the question is, how can we get this distribution? The idea of the variational autoencoder is to actually train the encoder part to encode not specific values, but distributions, something that we are telling, that we are specifying the encoder to create. For example, we can create the variational autoencoder so that the encoder part, when we present an example, gives us the mean and the variance of Gaussian distributions. For example, if we use several of these, if we have a multidimensional encoding, then this could be a multivariate Gaussian where all the Gaussians are distributed. So just to quickly go through this multivariate Gaussian distribution uses this covariance matrix for not only the variance along each of the dimensions, but also the covariances between the different dimensions. However, if we assume them to be independent, then this matrix will only have non-zero values on the diagonal. So each value on the diagonal will be the variance of each of the independent Gaussians that we have for each independent dimension. So this is one common type of distribution that we use in variational autoencoders. And basically the idea is we don't want the encoder to give us a specific encoding for an example, but to tell us what are the means and standard deviations of all these Gaussians that represent the distribution probability for that kind of examples. And this way, we learn the probability distributions to generate each type of example. So how do we do this in practice? The encoder will give us the parameters for probability distributions. Then, when we train the decoder, we are minimizing the reconstruction error, but first by sampling at random from these probability distributions that the encoder gives us. And we use a regularization term to try to make these distributions as close to independent Gaussians as possible. So the way we are going to do this is to change the loss function. We have here the reconstruction penalty. So basically we need on the decoder to get back the same input, the same X in the autoencoder when we're training. But we also include this Kullback-Leibler divergence between what we are obtaining on the encoder, the distributions that we obtain from the encoder, and what we would like it to be, this distribution, which is this independent Gaussian mixture. So basically, if we consider this a multinomial Gaussian, it would have only the diagonals on the covariance matrix, and there are no correlations between the different directions. So if we do this, then I'm not going to derive this formula, but this would be the expression for this Kullback-Leibler divergence between the variance and mean that we are getting from the encoder and this ideal, which would be a uniform, a Gaussian distribution with a variance of 1 and a mean of 0, and all independent in the different directions. So this is the basic idea. We are not getting from the encoder the exact values for the decoder. We are getting parameters for these probability distributions. Then we sample at random from those distributions and we decode from that sample. And we use this regularization term so that the distributions are as close as possible to these independent Gaussians. So schematically, this would be the variational autoencoder. The encoder part will, instead of giving us the exact latent representations for the input, will give for each input a mean and the standard deviation for the distribution along each direction. So suppose that we have a two-dimensional representation here on the hidden representation. So in that case, we would need 4 values from the encoder. 2 mean values and 2 standard deviations, so that we can specify the 2 Gaussian distributions that will output each of these values in the latent representation. And the way this works is that given an input, we would get the parameters for the probability distribution for that kind of image. And then we would sample from those probability distributions one hidden representation here at random, and then feed that into the decoder, and the decoder will have to retrieve the same image, or as close as possible to the image, from those parameters, from that sample, from those probability distributions. So this is the loss function here. This term is the reconstruction term, so the difference between the output and the input. And this regularization term here, that in this case, when we use these independent Gaussians, we'll have this expression, is just to make sure that the probability distributions we are getting here, these parameters, are as close as possible to the Gaussian with mean 0 and standard deviation of 1 that we want to use as a template. And this regularization serves to make the manifold here that these representations will cover more well behaved, so easier to sample meaningfully from and allow us to generate these images. Okay, so now we have a problem here, which is we are the encoder is giving us parameters for probability distributions, but then we need to sample at random to generate the output from the decoder. So the decoder is getting just a random sample from these distributions and not the actual values that the encoder is producing. And the problem here is that if we have the encoder module generating here a mean and a standard deviation, for example, and then we use these parameters to get a random example, a random set of values from these distributions, and pass this on to the decoder, we cannot backpropagate through this step, because we cannot compute the derivatives over a random sample. That it's not differentiable, that kind of operation. So if we were to do this just like this, we use the encoder to create the parameters for the distribution. We take one sample at random, feed it into the decoder and get the output. Then when we measure the loss function, we could propagate the derivatives all the way here, but then we cannot keep going, so we cannot train the network appropriately. This is solved by this reparameterization trick, which is to consider that the value that we are sampling and feeding into the decoder will be just the mean plus the standard deviation that we got from the encoder, but with the standard deviation multiplied by an epsilon, a random value that is taken from this normal distribution. So mean 0, variance of 1. In this case, the random step is only on this branch, but we don't need to backpropagate here. There is nothing to learn on this side, because this is just picking a value at random. This part, these branches, we can backpropagate because this is just a sum and a multiplication and so on. So backpropagation works perfectly through here, and we can keep training the encoder model. So basically, we can imagine that this is just an addition of random noise into this specific parameter for the standard deviation there. And so we can train the autoencoder in this way. So this is basically the trick. We need to rewrite this sampling step in this way so that backpropagation can work. And once this is done, we can train the autoencoder. So I'm going to show an example of how to implement a simple variational autoencoder. There are more complex variants, but this can be a very powerful model. For example, these multi-level variational autoencoders include different parameters for representing the distributions between groups of examples and within groups of examples. And this allows the disentanglement of the different aspects of the data. For example, in this case, with the NIST dataset, the authors created this multi-level variational autoencoder that encodes the examples into two distributions, one of which controls the content, so the kind of number that we are creating, this one on top here, so it can be used to choose if we want 0, 1, 2, and so on. And the other controls the style of the number. So if we combine, for example, the number 9 with this particular style, we get a 9 that is like italic and with a very narrow line. If we combine it with this style, we get a 9 that looks bold, and so on. So this is a more sophisticated version of variational autoencoders. I'm not going to detail this one, but this idea of instead of obtaining from the encoder a latent representation of the input, we want from the encoder a distribution for these representations. This allows us, by using this kind of regularization where we specify what kind of distributions we want, what attributes they have, and training this distribution, not only allows us to generate examples easily, but also to disentangle the different aspects of the data and then mix them together. The same thing with faces. There is the content and the style, and they can use, for example, one kind of face in different styles and positions and things like that, and they can mix these different aspects together by tailoring the different distributions to within groups and between groups differences. So let's see how we can implement a simple variational autoencoder using TensorFlow and cache. What we're going to do is create three models. We have the encoder. The encoder will output the parameters for those probability distributions. We have the sampler, which will sample from those distributions one latent representation, one example of a latent representation, and then the decoder that takes that particular vector for that representation and will output the original image, or as close as possible to the original image during training. But after training, we can just give it different representations and obtain different examples. We are going to mix up convolution and dense layers because we're going to deal with the MNIST dataset. And so these are images. We're going to use these kinds of layers, and we're going to use 2 dimensions for the latent space. So the sampler will output vectors of 2 values for each example. That's what the decoder will receive. And so the encoder will need to output 4 values, 2 variances and 2 means, because it has to characterize each of these 2 distributions. And we're going to use the regularization that we saw previously for this independent mixture of Gaussians. So this is just importing what we need, or probably a bit more than we need, and just have these constants. This is the original number of values in the images that we have. Remember that in NIST we have images of 28 by 28 pixels, so this is the dimension of the original data, and this is what we're going to try to shrink it into. So characterize each image by a pair of values, dimension 2. Of course, the encoder will have to produce 2 distributions, so we would need 2 values for the mean and 2 values for the variance. Okay, so now let's create the computational graph for the encoder. We're going to use the functional API for this. We have these inputs, so the shape of the input tensor will be 28, 28 by 1. This is a single channel image that we have. And we are going to receive here a list of how many filters we want in each convolution layer. And now for each of those number of filters, we're going to create a block of convolutions that in this case I put 2 convolutions so that we have effectively a 5 by 5 convolution, but we are decomposing it into a stack of 2 3 by 3 convolutions. I think this is a bit of overkill for MNIST, but it serves as an example for those kinds of tricks we saw previously, where we can reduce the number of parameters that we need for having a wider receptive field if we stack 2 small convolutions instead of using a large one. But this is, you can, if you want to follow this example, you can create different architectures. But the idea is that we are now going to create these blocks that have convolutions and pooling for each of the element in this list, which tells us how many filters we want to use on these convolutions. This last convolution width variable is just a convenient variable so that I don't have to recompute everything on the decoder, but it just tells me how wide is the feature map when I reach the last convolution. So each convolution block here is followed by a max pooling, and so with this size 2 by 2, so it reduces the feature map by 2 in each dimension. And so by using this, I know after I create all these convolution blocks, I know how wide the feature map will be. This is useful for the decoding because I then have to start from this feature map and revert all these operations. So now I'm going to flatten everything. I'm going to add a dense layer with this number of neurons. And then we're going to, from this dense layer, we're going to output 2 values. One will be the mean vector. So this will have two values. It will be a vector of size 2, which is the latent dimension that we chose here, and it will contain the means for the different probability distributions, the different Gaussians, and this will be the variance. However, we are going to use the logarithm of the variance, and the reason for this is that I'll skip ahead a bit. Variance must be larger than 0. It doesn't make sense to use a negative variance. We have a linear output on those neurons because we don't want to constrain arbitrarily that value, but we can consider that the output is the logarithm of the variance. So if it's negative, it's below 1. If it's positive, it's above 1. But then we just use the exponent of that to get the variance. Also, this makes it a bit more stable for all the numerical computations. It avoids problems of having to cut this distribution, for example, at 0 or something like that. So this is the idea here. We're going to output these parameters, the mean and the variance. It's actually the logarithm of the variance, but then we will convert it. And so with this latent dimension of 2, we have this output here. 2 values for the means of the distribution, 2 values for the variances of the distribution. And note that we are creating 2 dense layers that are both connected to the same output of the previous layer. So this X here is the result of this activation here on this dense layer, and then batch normalization just to speed up training a bit. But this is what we are getting into each of these dense layers. So we are following this scheme here, where these orange ones are getting the input from this layer, and these blue ones are getting the input from this layer too. So this is the encoder, the graph for the encoder. Then we're going to create the sampler, and the sampler is just a very simple model that takes receives as input the means and the logarithms of the variances, and then outputs this sample, this example from those distributions. So what we're going to do this is we are going to create this random variable here. We're going to use the random normal. By the way, this k here is usually an alias that is used for the carriage backend, which is another way of accessing some of the basic methods in TensorFlow, although it has the advantage of being independent from the backend that you're using. So if you happen to use carriage with Ceano, for example, you would still be able to do this. So we are getting there the random sample here, sampling from a normal distribution. We want this to be shaped as the number of examples that we have. Remember that when we are training, we are going to receive batches of examples. So the first dimension of all of these tensors will be the number of examples we are training in the batch. So this will be the number of random values that we are drawing, and we will have this we will use a random distribution with a mean of 0 and a standard deviation that in theory it should be 1, but if we use a very large standard deviation here, we'll be adding a lot of noise to the input of the decoder, and this will really make training harder. So I cheat a bit and reduce this variance here to a small value like 0.1 for the standard deviation, so that we have a bit of noise in this step. So we are doing this with a random epsilon here, but we don't use such a large variance for sampling this noise, so that it's easier for the decoder to train. But this will depend a bit on the model, and you can fine-tune this if you apply this to different problems with different models and so on. So now from the sampler we are going to return these values, the sample that we have here, and we can also return the means and the variances from there. We'll see how to put this together later on. But basically, we are returning the inputs and the outputs of this computational graph, and the same thing is happening here. When we create the encoder, we also return the tensors, the input tensors and the output tensors for this graph, in addition to this measure of the width of the feature map. And now we need the decoder. So for the decoder, again, we create the input. The input will be shaped according to the latent dimension. So in this case, it's a vector of size 2 for each example. In training, it will actually be a tensor, which in the first dimension will have the number of examples in the batch, but this is the basic dimension of each example. And now we are going to do the reverse of the encoder. So we start with this dense layer with the number of neurons we want in the dense layer here. So if we go back to our scheme, this would be the equivalent of that dense layer there. We are receiving this as input, so we start with this dense layer, and now we need to recreate the feature map. So we are going to create a dense layer that has a width and a height taken from the dimension of the last feature map that we obtained after the final pooling, and we'll have a depth with the number of filters that we have on the last convolution. So this is the last number of filters there. We create this dense layer so that we can map from the 2 dimensions there into this, from these dimensions here given by the dense neurons, into what will be the feature map once we reshape it. So this will give it the same shape as the last feature map here on the encoder. You see, after the final pooling, we have something that is the dimensions are this width and height, the same, it's a square feature map, and it will have this number of filters, which is the last element in the filters array. So that's what we are doing here. We are using that dimension that we got from the encoder graph and the same number of filters. And now we're going to go back in the convolutions. We're going to do the upsampling and the 2 convolutions, and then keep doing this until we reach the end, the same original dimension. And in that case, we're just going to create this sigmoid activation. So after we do this final convolution with one single filter, so that as the output we get just the original image, and we give it a sigmoid activation so that all the values are between 0 and 1, and we have something that is similar to the original image. Okay, so now we have the 3 graphs, the encoder, the sampler, and the decoder, and what we need now to create the complete model for training is the loss for the variational autoencoder. So this loss will have 2 terms. One is the binary cross entropy comparing the output of the autoencoder and the input of the autoencoder. Basically, we are comparing all the pixels of the image in the output and the image and the input, and we are, for each pair of values, we are computing this cross entropy, and we get the mean of that cross entropy for all the pixels. But we also need this Kullback-Leibler divergence so that we force the distributions that we are generating to be close to these well-behaved Gaussian distributions with mean of 0 and standard deviation of 1. So this would be the regularization term here that helps us get a smoother manifolds and make it easy to sample then new examples. So we're going to basically write this expression. These are the logarithm of the variance of our distributions, so we get the expressions here using the logarithm of the variance. When we this should not have a logarithm there. This is a typo. So this is the actual variance here, but we can get there from the exponent. So and we have the square of the mean and the exponent of the logarithm of the variance to get the variance. But basically this is just writing the expression, and now we combine the two. And here this is something that you need to fine-tune for each example, because if you give too much weight to the regularization, then you can reduce the quality of the output, because you lose on the reconstruction. The autoencoder will start sacrificing the accuracy of the reconstruction of the images or of the examples in general in order to force those distributions to be closer to the 0-1 normal distribution. If you put too little weight on the regularization, then it's likely that your manifold will not be as neat, as well behaved as you want, and then you have trouble picking examples, picking latent representations if you want to generate new examples. So there is some balancing that we need to do here. According to some papers, using about, since this will be the mean binary cross entropy between these values, it should be between 0 and 1. If we use a 0.1 times this one, if this is not too high also, this seems to work more or less, but it may depend on what the actual problem and the model is. So you may need to fine-tune this regularization weight here to improve results. Okay, so now we need to put everything together and create our model. So we're going to create the three different graphs, the encoder, the sampler, and the decoder, and we are going to create these models. So for the encoder, we use the input, and the output will be the z mean and the log of the variance for the hidden representation distributions, and then the sampler will receive these as inputs and output a sample, and the decoder will have its own inputs and output, the decoder output, which will then compare with the input in the complete variational autoencoder. So basically we have three independent models here, but they can be fit together in this way. We can create the output tensor for the variational autoencoder by applying the encoder model to the inputs, then applying the sampler to the output of the encoder model, and then applying to the decoder to the output of the sampler. So this is where we connect all of these computational graphs, and we now have a chain, a graph that goes from the inputs to the outputs of the variational autoencoder, chaining together all of these different models. So this is one example of how you can do this. You can break down your network into sub models and then chain them together. As long as the number of tensors in the input and the output match, you can do this. And now we can create the variational autoencoder model just by using this graph that we created here, connecting this tensor, the input tensor, to the variational autoencoder output tensor. And now we create a model from that, which goes from those inputs to those outputs. We also need the loss function. So basically the loss function will be this function here applied to these tensors. Note that we created this graph, so we have all of these tensors as part of the graph, and now we can create a loss function that takes the inputs, the outputs of the variational autoencoder. So this is where we're going to compute the reconstruction error, and also the means and the log variances obtained from the encoder. These are the outputs of the encoder. Now this is a trickier loss function, because so far we've seen loss functions that take into account the input and the output. For example, those binary cross entropy and so on. This one uses more tensors because it has to look at the output of the encoder inside the network in order to evaluate the Kullback-Leibler divergence. So when we compile our variational autoencoder, so in this case we're going to call the create models function to create all of these different models. We can compile the encoder and decoder. This is just This doesn't mean anything. The loss and the optimizer, in this case, it's just to fill in those parameters, because we are not going to train the encoder and decoder separately from the rest. They will only be trained as part of the variational autoencoder, but then we may want to use the encoder to get parameters for a specific example, or the decoder to generate some examples. So we want to compile them, but we are not going to train them, so the loss and the optimizer is irrelevant here. This is the specification of the architecture that I'm going to try here. Actually, this is 0.1. So this is one convolutional block using 8 filters per convolution, and then another one using 16, and then 16 dense neurons. This is an example of what you can do. This is for creating those models, and I use the epsilon sigma of 0.1. This is the cheat here on the sampler, so that we don't have a large standard deviation when we are randomly sampling from those distributions. So bringing this together, creating this, now training the autoencoder. This is just loading the MNIST data, reshaping it to the shape we are expecting, and dividing by 255 so that all the images are between 0 and 1. And now we train everything, and we can visualize the map. For example, just plotting the mean values for the two distributions for each example that we can get on the test set by predicting the parameters for the probability distributions on the encoding of each example in the test set. And then we can plot the parameters for the means so that we see how the means are spread out for all the different examples. This is the result of that plot. So for different digits that we have here, we see different regions in this parameter space where the encoder produces the mean values for the random distributions of those examples. And we can also look at the manifold that we generate. Basically, what I'm doing here is using a 15 by 15 grid. I create a set of values using the means from the different points in the grid. So you can imagine that this would be at the center 0 of mean for the first distribution, 0 of mean for the second distribution, and then we increase here the mean for the first distribution. If we go on this side, if we go down, we increase the mean of the second distribution. Going up, we decrease. So basically, we are looking at examples taking from those distributions in 2 dimensions by changing the mean to negative values and positive values for each of them around 0. So the way we can get these, generate these numbers is to create that value, so the pair of values, as if we were taking from that random distribution, but we are only considering the mean, not the variance, and then use the decoder to generate an image there. And we write the image to the appropriate region on our larger picture, and we get all the generated images like this. So this gives us an idea of the manifold around 0. Remember that we use this regularization, the Kullback-Leibler divergence, to try to force our distributions to have a mean close to 0 and a standard deviation close to 1. And this, in fact, when you see here the plot of the mean values for all the distributions we obtain for all the examples, we see that they are close to 0. They range from about -1 to 1 on both dimensions, but they are all here around 0. So this is what we get if we translate this back into numbers using the decoder to generate these numbers. And you can see how the manifold is spread out here with the zeros there, 4, 7, 1. So the different kinds of the different numbers, and also different ways of writing the numbers, different looks for the numbers. So this way, after you train the variational autoencoder, you can use the distributions for the different numbers to generate examples of ones, of zeros, of sevens, and so on, just by looking at the parameters you're getting for the different kinds of numbers. And since the manifold is well behaved like this, it's easy to sample in this latent space examples that will actually translate into meaningful outputs, into meaningful images on the output. Okay, so this was one example of variational autoencoders that we can use to generate images. We're going to look at a different approach, which is generative adversarial networks. So the problem, going back to what we saw before, is that if we want to generate something from the latent representation, we need to pick the right values on the latent representation. If we use a variational autoencoder, this is easy because the manifold on the latent representation will now be very well behaved, and we can pick the values if we want. But in general, we may not have a well-behaved manifold, and so picking at random there will often get us outside the set of values that would produce meaningful output. So one thing that we can do is let us consider that this hidden representation, this latent space, has a given distribution. Instead of trying to find those distributions using that regularization that we saw in the variational autoencoder, where for each kind of example we get a different set of parameters for the distribution, we fix these distributions. For example, this is a mixture of Gaussians with mean 0 and variance 1. That is fixed. Now the trick is to train the decoder so that from sampling from that distribution will result in some meaningful output. In the beginning, if the decoder is not trained, then we can sample from that fixed distribution, but the output will be garbage because all of these transformations here will give something that is probably not meaningful. So what we're going to do is we're going to also train a network that is going to distinguish between what the decoder is generated. So this decoder will actually, we can call it the generator because it's creating images, but it's mapping from this latent representation into the images that we want. And we're going to train another network, the discriminator, that is going to learn to distinguish between what the generator is producing, so the fake images, from the real images in our training set. And now what we're going to do is to use one network to train the other. So basically we're going to use the generator to generate fake images and then train the discriminator to classify them accordingly, to classify correctly the real images from the data set and the fake images generated by the generator. But then we're going to train the generator to fool the discriminator by creating better images that the other one cannot tell from the real ones. And so we're going to alternate this, and this will result in the network becoming increasingly better. So this is the state-of-the-art approach to image generator nowadays. And you can see some simple examples in 2014 of generative adversarial networks. But currently, we have very realistic examples, and you can see websites with synthetic faces, for example, or even for fashion models and things like that. So where whole people are created synthetically from these training sets, but using these kinds of networks. So the result can be quite realistic. Of course, the actual models used here often use multiple resolutions and other sophisticated tricks. I'm not going to go into those details, but I'm going to show you a simple application and a simple implementation of generative adversarial networks to illustrate how this works. But basically the idea is that we're going to force the generator to map from the initial distribution that we chose, these mixture of Gaussians, for example, and we are going to force it to learn to map this correctly into similar things to our training data by using the discriminator to keep training the generator. So the discriminator will be what the generator is going to try to fool. So let's see how we can implement this. We are going to create the discriminator model, and this is going to be trained to distinguish between true and fake images. We're going to create a generator model that inputs a vector of random values, these Gaussian normally distributed values, and generates the image. And we're going to train them combined with the discriminator. So basically, the discriminator is trained on the side in parallel on mixtures of true and fake images. The generator will be trained connected to the discriminator, but the discriminator will be frozen. This is one technique to help us train the generator to fool the discriminator. So let's see how we can organize this in encoder. I'm going to use the sequential model here. So this is the basic idea again. We're going to start, the generator is going to start with a dense layer first. This will have, so the input will be given by this latent dimension, for example, 100 or something like that. It's the vector of random values that we're going to feed into the generator. And then we're going to create the first feature map for the convolutions to start upsampling until we generate the image. So basically, we're going to create a feature map that is 7 by 7 and has 128 filters. We do this the same way we did before on the decoder, which is we create a dense layer with the right number of outputs, of neurons, and then we reshape that into the feature map that we want. So 7 by 7 with 128 channels. And now we're going to use upsampling and convolution, those kinds of techniques that we saw before, to go from this 7 by 7 feature map with 128 channels until we get the final one, which will be the 28 by 28 feature map after this upsampling here, with just one channel at the end. So this will give us the output, and we're also going to use the MNIST dataset, so it will be 28 by 28 with a single channel because it's a grayscale image. Of course, this is something that you can play with. You can use different models here. For example, in this tutorial that I based this example on, they used transposed convolutions. I changed this to the upsampling and convolution because it avoids those kinds of artifacts that we saw with the transposed convolution. But you can do this in different ways if you want to experiment. But the idea is just that we start with a vector of numbers, this random sample, and we end up with an image of 28 by 28 after the appropriate upsamplings and all these convolutions, so that the generator can generate the appropriate image. Now we need the discriminator. This discriminator is simply a convolutional network that classifies images into fake or real. So we just need one output here, one neuron with a sigmoid output. We're going to use the binary cross entropy for this model, and we just add the convolutional layers and flatten here to get the dense layer. You can use pooling if you want. In this case, this is a very simple network that doesn't have pooling. It just keeps building the convolutional, uses these convolutional layers to create the feature maps, and then just uses this final neuron as a linear classifier with those features. But you can make the discriminator more sophisticated if you have more complex problems to solve. This is just sufficient for this kind of problem with NIST. Note here a difference that we are compiling the discriminator because we're actually going to use this model and train the discriminator on its own in order to so that it can learn to distinguish between real and fake images. But we are not compiling the generator because we are never going to train the generator alone. That would not make sense because if we train the generator alone, we don't have a way of backpropagating the error into the generator. We need to train the generator connected to the discriminator so that we can evaluate all the generator part depending on what the discriminator is deciding. So I'm going to explain this a bit better later on. So basically now we're going to define the GAN model, which combines the generator and the discriminator, but in this case the discriminator will not be trainable. Now this is, remember that we did this with the transfer learning on the fashionist example, where we looped through all the layers on the previous model that we had trained on the fashionist, and we set for each layer the trainable flag to false. This is something that you can do even after the model is compiled, and you can just flag each layer if you want to train it or not. But if you are going to compile a model, you can just set the flag for the whole model to false, and when it compiles, it sets all those layers as not trainable. So the difference here is that this instance of the discriminator is trainable. We have all these tensors passing through these different layers, and we compiled the discriminator. And now we're going to take this model, we're going to set trainable to false. This is not going to change the model itself, those trainable layers, because this flag will not change anything after the model is compiled. But when we now compile a new model using the same tensors as this one, because we added this model as a new layer here to our GAN, then when Keras compiles this model, it will look at this trainable flag, and so in this particular instance, in the GAN, the discriminator is not trainable. It has the same tensors inside the GAN as it has when we create it here, but when we are using it independently, it's trainable. When we are using it inside the GAN, it's not trainable. So inside the GAN, the only thing that is trainable is the generator model. And we are going to use this to train the generator model by connecting it to the frozen discriminator, so that while the generator is learning, the discriminator is only saying if the image looks real or not. And that will be propagated to the generator. But this is the trick here. We are creating a model that is trainable, but we are then including it into a larger model where that model is frozen. So now we have two models that we can train: the discriminator alone and the GAN with the generator that is trainable and the discriminator that is frozen. So now let's bring this together and generate these things. So we have, we can choose the latent dimension. This is the size of the vector of random numbers that we're going to feed into the generator. We create the discriminator, we create the generator using this dimension here, and then we create the GAN by combining together the generator and the discriminator, but with this trick that we freeze the discriminator inside the GAN. The discriminator can be trained, it's already compiled, but when it's inside the GAN, it's frozen and it's not trained. Okay, so now we just load the data, we use the training set and reshape it. Note that we don't need the test set, we don't need the labels for NIST, we just need the training set to tell us what the real images look like, so that the discriminator has something to train against what the generator is producing. And now we train everything. So how do we do that? We're going to alternate training the discriminator and the generator. And the idea here is that we're going to do a number of epochs, for example, 100 epochs. We have this batch size, 256. We're going to create batches for training the discriminator that contain 1/2 of the batch has real images, and 1/2 of it has fake images generated by the generator. So this creates the batch for training the discriminator, and now we are going to stack these two together, so to create the batch of real and fake images. The fake images will have a target output of 0. The real images will have a target output of 1 on the discriminator. So now we train the discriminator on this batch. This can be done using this method on the model. So far, we've been running the fit method that just does a number of epochs and lots of batches and so on and takes care of everything. But in this case, for the GAN, we need to break down the training in single batches because we need to train the discriminator and the generator alternatingly. So in this case, we're going to train the discriminator on a single batch, and this batch is composed of real and fake images. And so it's going to learn a bit how to tell them apart. And now we're going to just generate a set of these random points, these latent points here, so that we can feed this into the GAN, into the generator, and make it so that the generator can learn to create images from these random points that fool the discriminator. So the target output for the GAN, which is the output of the discriminator in the GAN, will be 1 for all of these fake images. But when we train the GAN in one batch, we are only training the generator. Remember that we froze the discriminator on the GAN. So actually what we're doing is we're training the generator to create images that result in an output of 1 on the discriminator. That is, the discriminator is thinking that they are real images. Whenever this fails and the output is 0, we propagate all that error and update the weights on the generator. Since the discriminator is frozen, in this step the discriminator is not changed. And now we're going to alternate this for each batch, and we're going to do this over 100 epochs or something like that, and we keep training the two side by side. So let's just look at these different functions. The generate real samples just picks a random set of examples from the data set. We could do this a bit more sophisticatedly by going through the data set in order, or using first shuffling and then selecting blocks or something like that. But this is the simplest way to implement this. Just pick a set of examples from the training set and return those images and the labels 1, because these are the real images and the discriminator should output a value of 1 for the real images. When we create the fake samples, we first generate these random inputs for the generator. So this is just a sample of values from the random distribution that we're going to reshape so that we get this in the shape of a batch of examples, the number of samples and in rows, and the columns will be that 100 value, 100 elements for each example. And now these random vectors are going to be fed into the generator so that it can, using predict, it can tell us what the images are that it generates. So basically we can create fake samples like this for feeding into the discriminator model and training it to tell real and fake samples apart. When we are training the generator, by training the complete GAN, we just feed into the GAN the random values and let the generator try to fool the discriminator that is attached to it in the same network. Okay, so this is what happens after the first epoch. This is an example of the kind of images that the generator can output after one epoch. It seems a bit like numbers, but it's very far from being actual numbers. After 25 epochs, both the discriminator and the generator have improved, and now the generator is already outputting things that look like digits, although a lot of them still don't look like it. After 50 epochs, it's improved, and we can keep training. So the idea is that since we are training both the discriminator and the generator, the generator has to keep improving in order to fool a discriminator that is getting better and better at distinguishing these images, and so we start generating better outputs from the generator. So to sum up before we take a break, variational autoencoders. The encoder part tries to learn parameters of probability distributions. So for each example, it will output a set of parameters, but not the encoding itself. The encoding will be a random sample from that distribution, and that is what is fed into the decoder to recover the input. Using a regularization term, the Kullback-Leibler divergence, we can force the distributions that we are learning to be close to some target distributions that we want. For example, independent Gaussians, and this helps make the manifold better behaved, and so we can then use it easily to generate new examples. There are other applications, other sophisticated variants of variational autoencoder that have additional properties like disentangling the different aspects of the data and so on. So this is more than just for generating images. And of course, all of these models can be used to different types of problems, for dealing with time series, for dealing with three-dimensional data and so on. It's not just for images. I just focused on images because we've been covering images so far, and it's the most intuitive kind of example for these kinds of models. Generative adversarial networks. In this case, we fix the distribution for that latent representation. So we decide, for example, in our example here, that this would be 100 independent Gaussians. That is fixed, and we can sample from that to generate examples. But now what we need to do is to train a generator network that can map from that distribution to something that is meaningful, to examples that are useful to us. And to do that, we're going to train it adversarially. We're going to train it in parallel with a discriminator that can tell if the image is fake or real. And both of the networks will improve by training them alternating one and the other. And so eventually, after a number of epochs, we start getting some more quality results from the generator. So there are some sections here in the textbook for variational autoencoders and generative adversarial networks. If you are interested in generative adversarial networks, the same author of this tutorial that I based this example on has a book on generative adversarial networks with Python. If you want, there are lots of examples there. But this is not part of the course. This is only if you are interested in getting a deeper understanding of this kind of models. Okay, so let's take a short break and we continue at 10:15. See you soon.